Hello. Okay, I think that was the bell. Okay, so let's get started. Any question from this time? Okay, so the quick review of this time. This time we talk about 5.5. We talk about orthonormal set, or orthonormal basis. So orthonormal basis is a basis where every vector is normal. Means that they have length 1, where length is defined by the inner product. So go back a little bit. So orthonormal basis is defined on an inner product space. Because on inner product space, we can define angle and the length of vectors from the inner product. Okay, so we can now define orthonormal basis. Okay, so the length is the square root of inner product square of inner product of a vector with itself. And orthogonal means two vectors that has inner product 0. Then we can now define orthonormal basis. It is a basis where every basis element here is normal, means that their norm is 1, and every pair of them is orthogonal. And we have seen the property that orthogonal is a stronger property than linear independent. So if vectors are orthogonal, that means they are linear independent to each other. Okay. So orthonormal basis is really nice because it's a lot easier to calculate things on it. For example, so it's basically all the properties stem from here. So if you want to calculate the coordinate on an orthonormal basis, then it's just so coordinate of some vector x here. Then the coordinate on this basis is just x inner product with uy. That's the ith coordinate of x. Okay? And so you can do this from 1 to k, and you will see all the coordinate. Okay. So that's from this time we see orthonormal basis is nice. And this time, okay, so now we have something to try is this Gram-Schmidt process. And it is a way to construct an orthonormal basis. So we now give a very constructive way to get the orthonormal basis. And so this process says that you start from some whatever basis, not orthonormal, then you can always get the orthonormal basis, and that's been the same vector space. And okay, so let's go into the process. Okay, so this is kind of the construction and the proof. And so remember our idea is we want to construct this u1, u2 to un from x1, x2 to xn, such that u1, u2 to un is orthonormal, and it also spans the same space as x1, x2 to xn. Okay, and we do this step by step. And so here we from 1 to n, and here from 1 to n. So we actually show that show that our u1 to u1 to un has an even stronger property than they together span the whole space. Okay? So we say that so you take any k from 1 to n, then u1 to uk will span the same space as x1 to xk. So this is n different equalities. So it says that you first take the first k element of this set and the first k element of the set for any k, then they will span the same space because we construct this u1 to uk one by one. Okay. And so because this is true for 1 to k, so kind of this is true for 1 to n, then with k equal to n here, then the whole set will span the whole set. Okay. And so the proof is kind of inductive. So we will go like on the k plus 1, we'll use this property and say this is also true for k property for k plus 1. Yeah. Okay. So let's construct this step by step. So first step, we want U1 to be also normal set, and U1 to span as X1. Okay. And what we do is we just normalize X1. So we define U1 as X1 normalized. And so U1 is normalized, and there is only one thing in the set, so it's orthogonal to itself, not itself, but there is nothing else to compare, so this is also normal set. And span U1 equal to span X1 because, well, U1 is just proportional to X1. So every linear combination of X1 can be written as a linear combination of U1. You just multiply HR X1 on the coefficient. Okay, so this is a trivial step. Okay, and the second step is basically everything. So we see this a little bit, and now we see this more careful. Okay, so second step, now we have U1. Okay, and then we have this starting induction step. So we know span X1 equal to span U1. Okay, so what we think is, so we have those two things the same, and then now we try to add X2 onto both of the sets, kind of. Okay. So we now add X2 onto this span X1 equal to span U1 space, and see how the space goes. Okay. And yeah, so we want to add HR U2 in this span U1 U2. We want to add HR U2 such that span U1 U2 will contain this X2, so yeah, and that will give us span X1 X2, span X1 X2, same as span U1 U2. Yeah. So we think there is this U1 X1, this span U1 space here, and we have HR X2, and so the HR thing we want to add is, so we want to add something that contains X2, but that's also going to U1. And so if you draw a picture, then you see that you kind of want to project X2 onto U1. So there is some P1 here. And then the remaining part, it will be something orthogonal to this U1. Okay. And that's exactly what we do. So we define this projection. So P1 equal to X2 union product with U1 on U1. Okay. And so this is basically writing X2. So this is the projection, and once again, it's kind of like this thing. So we say like something on the coordinate of a vector onto some orthonormal thing is inner product. So it's a bit similar calculation here. So you have the coefficient as X2 inner product with U1. But anyway, the coordinate is this, then you times U1, and as we've seen before, this is a projection, and we have proved this in a theorem, and proved this in the latest theorem, theorem 5.5.7, says that if you take this projection, and so you get rid of this projection from X2, then the remaining part will be orthogonal to your projection vector, which also means it's orthogonal to this U1 vector. Okay. So this is writing the geometry in algebra. Okay. So yeah, so you take a projection and you get rid of projection, and the remaining part will be orthogonal to this projected part. Okay. And okay, and yeah, and then we want to, so now we want to normalize this part to say this is our U2, and but to normalize it first, we need to say this is not actually 0. Okay. So why is this not 0? It's from X2 is linearly independent. Okay. So it's like what we want to try to prove here is show is that X2 is not just proportional to U1, right? If X2 is proportional to U1, then there is no HR component here. So we want to say the HR component is not 0, and it's from X2 linear independent with U1 or X1. Okay, and yeah, so we just say this part is okay. So X2 minus P1. So we go back to linear independence of, okay, so actually linear independence of X2 and X1, okay, because U1 is proportional to X1. Okay. And anyway, so we write this X2 minus P1 as some linear combination between X2 and X1. So X2 minus P1, and P1 is proportional to U1 and U1 is proportional to X1. Yeah. So this is a linear combination of X2 and X1. Yeah. And well, because X2 and X1 is linear independent, so this thing is zero if only if every coefficient here is 0. But you see the coefficient between X2 is 1. So this thing is not a zero vector because you have a non-zero coefficient of 1 here. Okay? So X2 is, so this X2 minus P1 is non-zero, so we can normalize it. So it has no another 1. So now finally we found U2 here. Okay? And okay, so let's check U2 satisfy all 3 properties we have. So first, U1, U2 need to be also normal. Okay, and okay, so by construction here, so U2 has known 1, and also we want the U2 to be perpendicular to U1, and that's also true from our construction here because U2 times some power of U2 is perpendicular to U1, and yeah, so because this thing is proportional to U2, so U2 and the perpendicular is linear. So U2 is also perpendicular to U1. Okay. So U1, U2 is also normal. Okay. This is the first thing we check. And the second thing is we need to check this this induction thing we have is also true. Okay. And here we just say U1, U2 is also normal, so it's also normal basis of something. Okay. Because they're also normal. Okay. And it's also normal basis for what? For span x1, x2. Okay, because they are inside x1, x2, right? Okay, so here this basis, I guess we need to say a little more. Okay, so span of this thing is 2-dimensional, and the span of this thing is 2-dimensional, and they are linear independent because they are orthogonal, and there are 2 of them, so this is the basis for this whole space. And okay, and I guess the extra thing we need to say is U1, U2 is inside this span, and that's pretty clear because U1 is inside span of X1, and then U2 by the construction here, U2 is a linear combination of X2 and X1, so U2 is also inside the span. So those 2 things are inside this space, and they are linear independent, so they are basis for this span. Okay, so there are bases for this span, and then their span equal to the whole space. Okay, and that's the second one. And then basically the next one, so that's how you find the second vector. Then the third vector, basically you do the same thing. Okay, so here we do very short. So yeah, so when you get the x3, then you want to find the part that's projected on span of x1 and x2, or span of u1, u2. Okay, so let's write that here. Okay. So this is span of x1, x2, and also equal to span of u1, u2. Span u1, u2. Okay. Okay. So now you have some h3, h4, and so it's linear independent to this space, so kind of stick out, and then want to find the orthogonal component that stick out. Okay, so once again, what we do is we find the projection onto this space. We want to find the projection onto this space, and then get rid of the projection part, and the remaining part we think then by our theorem 5.7 this will be orthogonal. And projection as we prove in 5.5.7. So maybe let's go back. Where is our a little too much. Okay, yeah. So once again, so reminder 5.5.7 we say if I have also normal basis on this space S, then we want to find a projection onto it. Then we just say it's the sum of the coefficient and this also normal basis. And where the coefficient is the inner product with your vector and the basis element. So you need also normal basis here but we do have also no basis here. This is U1, U2 here. Okay. So to find the projection onto this span U1, U2 is easy. You do the formula of just C, and we write down here. So it's X3 inner product with U1 times U1, X3 inner product with U2 times U2. Okay. So this is a projection of X3 onto this space that we already found. And then we subtract this from X3, and this part will be orthogonal to this span. And then basically the same argument goes. So we normalize this vector by dividing its norm. And now this thing is norm 1, and is orthogonal to U1, U2. So U1, U2, U3 is also normal basis for for the span is also normal basis for the span of x1, x2, x3, and because they are also normal basis, then span u1, u2, u3 will be equal to span x1, x2, x3, and then you can see that we can repeat this from to all the vector up to until we go through every vector, and we'll get also normal basis for our space spanned by these n linear independent vectors. Okay, so that's basically the proof and the process of proof and step. So we have a proof and step together of this Gram-Schmidt process. Any questions so far? Let's go to the next page for you to get questions. Okay, so this page we have the steps here written out. Okay, and you have the steps in more compact form. So we say that we have x1, xn is a basis for some space that has inner product. So inner product here is kind of important. You need to have an inner product to define orthogonal and norm, etc. Okay, so you can find the orthonormal basis from here by defining first. The first step is u1 just normalize x1, and from u2 to u1 you recursively find them. So you add in those x2 to xn one by one. So you want your uk plus. So if you already find u1 to uk, then uk plus 1 is normalized. This also normal part normalized, and the also normal part is you get rid of the projection onto previous part you already find, and then you normalize it, and the projection onto previous part is done by this. So you already find the also normal basis from x1 to xk. So you can find the projection onto a space spanned by x1 to xk by this easy. So you just take your xk plus 1, and the coordinate on u1 to uk is xk plus 1 inner product with u1 to uk. Yeah. So you can find. So you take xk plus 1, then you find the projection and get rid of it and normalize it. Then that's your uk plus 1. Okay. And so we find that we can have also normal basis for our space V spanned by x1 to xn. Okay, and okay, so this process is a bit annoying to do, but it has so aside from let you just do calculation and find also normal basis, this process actually also have a theoretical application, as we'll see today. Okay. And so important thing here is that because this process exists, this means that every inner product space has also no basis, right? Because or every finite dimensional inner product space has also no basis. That's because every finite dimensional inner product space has a basis, and you can just turn that basis into also normal basis. Okay. So there always is also no basis. And also something extra we didn't show here, but you can try yourself, is that if you okay, so I forgot to say this. I guess. Okay, let's say this first. And so we didn't prove, but you can try yourself, because it should not be too hard to show. Is that so? We had our x1 to xn is a basis, right? So here we have a basis, and everything is linearly independent. And but what if this thing is not linearly independent? Then you can still run the Gram-Schmidt process, because here and so you can still try to run Gram-Schmidt process, and what will happen is that when you run into something that's not linearly independent anymore, so say it is xk plus 1 is not linearly independent to x1 to xk, and what happens will just be that well, it's not linearly independent, then it's just equal to this projection, and that means uk plus 1 is you just take uk plus 1 as 0. Okay. So you can still run the process, and just on some linear dependent part you don't get the extra uk plus 1, and but so you will still find the orthonormal basis that's like that has the same number of elements as the dimension of this span. Okay, and that's actually very useful, because that's also a constructive process that you find the vector that's that's linearly dependent on the previous vectors. Right? So remember, when we do this, we go like when we do this before we, but it's like a harder version of Gaussian elimination. So I think this is a bit different from Gaussian elimination, but you can see the spirit is similar. So when we do this before, we were saying like, if you want to find the HO, like the maximally linear independent set from span of this thing, then we like list them as a matrix, and try to do Gaussian elimination. But here you see there is another way you can run Gram-Schmidt process through them, and you will get a basis, and it's not only a basis, it's also normal basis. Okay, so it's even a bit nicer than what we found from Gaussian elimination before. Okay, yeah. So before, okay, so a little reminder. So before we were finding a basis for this x1 to xn, we were saying, okay, so there are kind of two ways you can listen as rows or as columns. Okay, right? So let's say if you listen as columns, then you do Gaussian elimination, and you need to find the pivots, and the pivots will correspond to the actually the minimal set that will span the whole space. But okay, so you will find some basis from that's equal to x1 to xn, and Gaussian elimination is a little different, in that you will find something that's probably also you will find something that's also linear combination of those, but it's also normal. Okay, so that's the Gram-Schmidt process, and that's the example of actually calculating this. And so it's exactly this. And I guess it's different because we have a linear independent. Okay. And so this is a nice example. So we want to find the orthonormal basis for the column space of this thing. So we want to find the orthonormal basis for those three vectors. Okay. And here we have a nice example. Those three things are linearly independent. So we will actually find a three-dimensional orthonormal basis. Okay. And so let's just go through this with numbers. Okay, so first vector is O1 vector. Okay, anyway. Oh, I see. First vector is this O1 vector. And so as we say Q1, why do we say Q is there U? Anyway, we use Q is there U, but Q1 here is you just normalize the first vector. And okay, so first vector is 1, and its norm is a square of 1, 1, 1, 1, 1, and it's 2. And yeah, so Q1 is the x1 normalized, and it is 1 over 2, 1, 1, 1, 1. Okay. And Q2, as we said, we want to get rid of its projection onto Q1. Okay. And so projection onto Q1 is A2 inner product with Q1 and times U1. Okay. And so A2 inner product with Q1, we can calculate this pretty straightforwardly. And A2 is minus 1 for minus 1, and Q1 is our 1 over 2, 1 over 2, 1 over 2, 1 over 2. And we do a calculation. Okay, so let's check a little bit. So here everything adding together is 1 is 3. So 4 minus 1 is 3, 4 minus 1 is 3. So 3 plus 3 and divide by 2, so it's 3. Okay. And so P1 is 3 times Q1. And it's 3 over 2, 3 over 2, 3 over 2, 3 over 2. And okay, so you can see the calculation is actually quite complicated. Then now we are on the step where we already calculate P1, and now we're going to calculate A2 minus P1. Okay, so A2 minus P1 minus 1, 4, 4 minus 1 minus this 3 over 2, 3 over 2, 3 over 2, 3 over 2. Then we get this minus 5 over 2, 5 over 2, 5 over 2 minus 5 over 2. Let's see, is this correct? So 8 minus 3, okay, 5, and minus 2, 3, 5. Okay, and okay, so we can check a little bit. So this thing is actually proportional, is actually perpendicular to U1. Okay, right. So do we know? Okay, yeah. So let's check a little bit. So this thing is perpendicular to U1. So U1. Sorry, I forgot. So this is perpendicular to U1, so remember U1 equal, let's say U1 is about 1, 1, 1, 1, 1, 1, 1, 1, 1 times 1/2. And so we take inner product with this thing and 1, 1, 1, 1, then you see the negative cancel with positive, negative cancel with positive. So it's actually orthogonal to U1 as we want. Okay, so that's nice. We find the orthogonal component. And then we want to normalize this thing. Well, then we do calculation, and the number here is nice, but the typing here is wrong. Okay. So we are missing a few plus sign here. Okay. And yeah, so so I guess it's the same calculation before. So everything is 5 over 2 here. So you get 5 over 2, and there are 4 of them taking square root, that's 2. So 5 over 2 times 2 is 5 here. And yeah, so finally you normalize this with this 5, and you get minus 1/2 plus 1/2 plus 1/2 minus 1/2. Okay, and lastly, then want to do Q3, then it's even more calculation. So you want to find so our Q3, so our A3 is 4 minus 2 minus 4, 4 minus 2 plus 2, 0. So we want to find its projection onto Q1 and Q2. Okay, and the inner product is those two things. So inner product with Q1 is 1, 1, 1, 1 with 1 over 2. And okay, so it's 4, so minus 2 cancel with plus 2, so 4 divided by 2 is 2. And the inner product with Q2 is this thing. And let's see, so it's a lot of them. So it's minus 2 and minus 1, then plus 1. So that's minus 2. Okay. Okay. So we have to do those two coefficients, and then we do P2. That's the coefficient times Q1 or coordinate times Q1, coordinate times Q2, and it's this thing. And okay, 2, 2. Okay, so it's 1, 1, 1 minus 1, 1, 1 minus 1. So it's 2, 0, 0, 2. Okay, and lastly is orthogonal to sorry, 7. Okay, and yeah, and finally A3 minus is 2, 0, 0, 2. Then we got 2 minus 2, 2 minus 2, and it's orthogonal to both of those vectors. Because inner product with this vector, then you get plus minus cancel, and the inner product with this vector, then you get minus minus, and plus plus, so also cancel. Okay, so yeah, so this is orthogonal to both of those vectors as we want. Then finally, R3, and finally our U3 is you normalize this vector, and yeah, and the norm is 4, and you normalize to 1 over 2. So once again, you normalize to a whole bunch of 1 over 2. So 1 over 2 minus 1 over 2, 1 over 2 minus 1 over 2. And yeah, so those three are our Q1, Q2, Q3. Okay, so yeah, so Q1, Q2, Q3. And you can see the Gram-Schmidt process is quite a bunch bit of calculation here, but it does find us the also normal basis. Okay. And yeah, here is some note. So okay, here is we expressing everything backward. So we say A1 is R11 times Q1, A2 is is some coefficient, A2 is some coefficient to Q2, Q1, and A3 is some coefficient to Q1, Q2, Q3. Wait, I think here we probably have a typo. It should have Q3 somewhere. 3, Q3. 1, 2, Q1, 2. I think here this one is R3, Q3. But anyway, it's not too important. Just saying that you can express everything back. Okay? Okay, so we have 20 minutes. Okay, then let's see something funny. We go back. So that's the calculation part of Gram-Schmidt's process, and let's see the application of a Gram-Schmidt process more in the theoretical side. As we said, it's useful for just being exist, because then you can find also normal set. Okay, so let's prove this theorem that we proved before, but hopefully now we have easier proof now. Okay, so this is theorem 5.5.2, where we say you have some subspace S, and it's dual space. It is dual space S, not dual space, sorry, complement space S perpendicular. Then we say the dimension add up into n. Okay, and actually, if you join the basis, then we'll get a basis for your parent space. And before there was the Rn here, but now we can say those for general finite dimensional space then. Okay, and okay, and before our proof, we need to use the regularity theorem. But now we only need to use that we have Gram-Schmidt process. Okay, and yeah, so here we don't need to use regularity theorem. And actually, I believe you can kind of prove this backwards, so you can prove this theorem this way and use it to prove the regularity theorem. Okay, but anyway, let's see how the proof goes. And also the theorem statement I modified a little bit. So now that we say we have also no basis for S and also no basis for S perpendicular, then you join those two bases together, then you get also no basis for your parent space V. Okay. Okay. So say how does this go? So first we can find also no basis for S and also no basis for S dual. So for S perpendicular. And that's just because Gram-Schmidt's process exists. So because this process exists, so you can find a basis for S and turn it into an orthogonal basis. And similarly, you can find a basis for S perpendicular and turn it into an orthogonal basis. So you get an orthogonal basis here and orthogonal basis here. Okay. And but now we haven't have the dimension A to n thing. So so if we count the total number of orthogonal vector here is some number k that might be smaller or equal to n. Okay? And obviously we'll prove k equal to n later. But for now, let's just think about we have r vector here and k minus r vector here for some k. And now we think about this set altogether. So u1 to ur and ur plus 1 to uk. And so this set is orthogonal. And so this is where we use S perpendicular is actually perpendicular to S. This set is orthogonal because between all these sets, they are, well, by construction, they are orthogonal and to each other, and between them is orthogonal to each other. And between, so if you have like a closed term between the first part and second part, then because S and S, everything S and S perpendicular are orthogonal, so obviously those pairs are also orthogonal. Okay, so this is the orthogonal set, and by the theorem we start with 5.5. Then it's orthogonal, then they are all linear independent. Okay, so this is an orthogonal basis. I guess the orthogonal basis part is not too important here. And okay. Okay, so we are doing this in a bit funny order. Anyway, so it's also normal basis, but okay, it's also normal basis for whatever dimension and span. But so now there is still something the only thing we haven't proved is that k equal to n. So can there be some other vector that's not spanned by those but inside V? And we show it's not possible. Okay, so because if k is less than n, well then there is something that's linear independent of this thing. Because k less than equal to n, that means u1 to uk span something only k dimensional that not equal to the whole space. Okay, and yeah, so there is something that's there. So k less than n means u1 uk doesn't span whole V. And that means there is something in V that's linear independent to it. Okay, so there is some xk plus 1 linear independent to this set we found. And but this xk plus 1, so yeah, so we will try to prove by contradiction. So this k plus 1, then we can append it to this u1 to uk. And we run grand string process again. And we can find some uk plus 1 that's an orthogonal component of xk plus 1 to all those things. Right? Okay. And but now this uk plus 1 is really weird. So uk plus 1 is orthogonal to everything here. But if uk plus 1 is orthogonal to u1 to ur, that means uk plus 1 will be orthogonal to everything in S, right? Because everything in S is a linear combination of u1 to ur. And yeah, so this is an argument worthy thing when we, guess we can go back. So I think it's here, right? So this argument, we say that if we are orthogonal to every basis element of a basis of orthogonal basis, then we are orthogonal to that whole space spanned by your orthogonal basis. Okay, and yeah, so uk plus 1 is orthogonal to every basis element of S. And that means uk plus 1 is perpendicular to everything S, and everything else is perpendicular. Okay. But uk plus 1 is also orthogonal to this basis for S perpendicular. ur plus 1 to uk. And is perpendicular to everything, then it cannot be inside S perpendicular, right? Because everything inside perpendicular is a linear combination of those, but linear combination of those has zero inner product with this, so the coefficient must be all 0. Okay, so it's not inside S perpendicular. Okay, and so this uk plus 1 can only be 0, and that's a contradiction. So xk plus 1 is actually, yeah, so you cannot find the linear independent xk plus 1. And so we got a contradiction here, so that means that only thing possible is k already equal to n, and this u1 ur plus 1 uk is k is actually to un, and oh, why do I missing word here? Okay, so so this thing is also no basis for v, is on basis. Okay, yeah. So this is what I think that's most straightforward to prove theorem 5.2.2. And so I also have a reminder. Okay, but anyway, any question here so far? Okay. Okay, yeah. So, but here we also see that then we have a bit even nicer way to describe this S space and the complement of S. So you see that you have S and S complement, then you can find also no basis on S and also no basis on S complement. And if you just union those two bases together, you have also no basis for the whole space. Okay. And now a little reminder before. And before we also define this direct sum, we say you have a direct sum if your space W is the direct sum of two space, then kind of means that the basis of W is the union of basis for U and the basis for V. And but by the definition, this means that everything W can and uniquely be written as some U in U and some V in V. Okay. And then you can prove this, and then we show that V is the direct sum of S and S complement. Okay. And the proof here is similar to a book, but because here we don't actually use the fact that we have also normal set, but you can see this kind of nicely with also normal basis. Sorry. And so yeah, so we say S and S in particular, we can have also normal basis. So yeah. So we can write orthogonal basis for V with first R element, that's orthogonal basis for S, and the n minus R element is orthogonal basis for S perpendicular. Then you can find this U and V really easy. So U is just projection onto S, okay? And V will just be a projection onto S perpendicular. And then you need to kind of show that the projection is unique, but it's not too hard. Yeah. And yeah, as we said, is U and V are projection onto S and projection onto S perpendicular. And so the Ci will, as before, just equal to. Okay, so what's our vector? Our vector is W. Is the inner product of W with Ui. Okay, so here we give, I guess, a little more constructive proof. So, yeah, you can just project your W onto S and S perpendicular. Basically, you project onto this orthogonal basis, and the first part of projection will be projection onto S, and the second part of projection is a projection onto S perpendicular, okay, with those coefficients equal to inner product. And finally, we have this theorem, 5.2.4. And okay. So I guess the proof here, also we didn't use orthonormal, but I think this is a bit clearer proof than the textbook one. So we have the S property as complement is S. Okay. And this we can just count by the basis. So so our dimension of S equal to some R, and so by the theorem we prove here. So this theorem 5.2, we know the dimension of S dual is n minus R. Okay. So dimension that's right here. So by the theorem before, so okay, so let's say, okay, oh, it's a bit annoying to say because we didn't say the dimension here. So let's say this thing is dimension n, and then the dimension of S complement will be n minus R, and then the dimension of S complement will be n minus r, so it will back to r. Okay. And okay, so dimension is r, and then you can just say the u1 to ur we'll be talking about is orthogonal basis for S complement. Okay, so so first is linear independent, and secondly, obviously, it's orthogonal to everything in S perpendicular. Okay. And and yeah, so they are all linear independent, and it's inside S complement. So by by the theorem here before, then it's basis for S perpendicular S complement, and yeah. So S complement is spanned by this basis that's the same basis as S, and so those two spaces are equal. Okay, any questions? If not, then we will finish our edited version of 5.6. Yeah, and yeah, so this is what we want to talk about in 5.6. Although the book obviously didn't talk about the 5.2 thing again, but so you know the Gram-Schmidt process, it's pretty complicated to do. I think it's nice to remember it a little bit. Maybe try for some small example. And then theoretically, we know that just having Gram-Schmidt process exists, we can show that there is also no basis for every inner product space, finite dimensional inner product space. And also we see that we can have a nice also no basis for every subspace S and its complement. Okay. Any question? If not, then I think we can finish about 5 minutes early, because that's everything. Yeah. So yeah. So once again, this is everything we want to talk about in inner product. I guess we can review a little bit once again. So we have been talking about, so from the 5.4. So everything starts with the inner product. So we are talking, so we have derived a lot of results for abstract inner product. And abstract inner product is a function that's defined on two vectors. So you need to satisfy those three things. So it will be inner product with itself, every inner product with itself is 0 and greater equal and equal to 0 if only if the vector is 0. And this will help us define a norm from the inner product. And X inner product with Y is symmetric, so same as Y inner product with X, and the inner product is a linear in phase element. And so from inner product we can define, so first we can define a norm. So we can say norm, the length of a vector is the inner product square root. And then we can define angle between two vectors. So we say two vectors are perpendicular to each other if the inner product is 0. And also we have a more refined definition of angle. We can also say if you have two unit vectors, then their inner product is the cosine theta of their angle theta here. Okay. And but anyway, from the inner product we have angle, so we can define orthogonal and we can define length. And so on 5.5 we do this orthonormal set. On 5.5 we can define this orthonormal set, and we see that it's very nice. It kind of make basically everything back to R. So this orthonormal basis is like really like a standard basis for R. So you can find the coordinate easy. You just take an inner product of your vector with your orthonormal basis element, and then we have seen that somewhere here. Okay. So we can see that those coordinates. You can also define. You can also go backward a bit and find the inner product between two vectors in terms of the coordinate on your orthogonal basis, and it's just like what you have on N. Is some I, A, I, B, I. Okay, so orthogonal basis is really nice, and then finally 5.6 we show that you can always find orthogonal basis by this Gram-Schmidt process, which is you take your basis and try to construct orthogonal basis one by one. So you keep adding more element from your X set into your orthogonal set, and so you want to find the part that's orthogonal to the part you already find, and then you normalize this one and normalize this extra vector and add that to your set, and you just keep going until you go through your whole basis x1 to xn. Okay, that's exactly on time, and yeah, let's see you next Monday. And we should begin our teaching on eigenvalues next week. Okay. This is lesson about inner product space. Okay, so see you on Monday.